So it's classic, but so good. I will say it loudly. And again, we have these numbers related to the shape of that. And if we put these numbers into a generating function, so if we take the sum as m goes from 1 to infinity of the number of solutions of the equations defining this variety over these finite fields, then this is the logarithmic derivative of a rational function. Which is a product of polynomials whose degrees are given by the dimension d, are given by the Betti numbers of xc. So let's let bi be the rank of hi xc q, the Betti number, and then pi is the characteristic polynomial of the Frobenius acting on the ith étale cohomology and has degree bi. Moreover, the absolute value, sorry, bi. And the absolute value of these, it's the inverse roots. So this is pi is a product of over some roots, and let's actually make them these inverse roots ij of t, where the alpha ij are algebraic numbers. Of absolute value q to the I over 2. And this puts the zeros in the poles. They're the real part of the zeros in the, this is zeros in the poles if you make a variable substitution. So related to the Riemann hypothesis, the $1 million Riemann hypothesis in a straightforward way. One set of lovely applications of the Weil conjectures, which has just gotten recent energy, this 2025, is a program of Ellenberg, Venkatesh, Westerlund that got itself fixed and is moving forward. They have part that they did. And then there's recent progress also proving some conjectures that they made in the second paper, which looks at spaces of covers of P1, branched covers of P1, and has applications to Galois theory over function fields. So Ellenberg, Venkatesh, Westerlund, they apply this to Hurwitz spaces. So if you look at X, a Hurwitz space is a moduli space of some kind of degree D cover, maybe with a fixed Galois group of P1. So Hurwitz space, this is a moduli space of branched covers of P1. Sometimes you make them connected, sometimes you make them like a degree D, sometimes you make their Galois group a fixed group. There are lots of little flavors of Hurwitz spaces. They're also, they could be a closure in the last talk of the M bar, zero, you forget the mark points, then P1D, for example, you can construct them like this. So we've seen a flavor of Hurwitz space in the last talk if you take a closure in that locus, and there are other flavors, but understanding the geometry of the complex points, so they compute the BI for x of c, and they make this translate into using the Weil conjectures into knowledge of sizes of fq to the m points. And so here's the Weil conjectures, and then they get stability results. This is on topology of these moduli spaces, allowing one to understand stable cohomology of XC translates into results on the Cohen-Lenstra heuristics. And just the existence of covers with a given Galois group for function fields. Their first sort of breakthrough paper has this sort of sample application in it. So this is a theorem of Ellenberg, Venkatesh, Westerland, done with this sketch summary program. So L odd prime A finite abelian group of order of power of L. Let's say Q is not congruent to 1 mod L. So then as Q goes to infinity, upper and lower densities of extensions of FQT, whose class group has L part A, is what's predicted by being a random group. So as Q approaches infinity, the upper and lower densities of quadratic extensions or of FQ of T. Here's our function field of P1, the particular flavor of Hurwitz space. We've got ramified at infinity. And then the L class group, the part of the class group, which is the L group, is going to be isomorphic to A. And then that's about 1 over the order of the automorphisms of A, as though you were picking randomly. Ramified at infinity with L class group. Isomorphic to A. Converge, they both converge to one over the size of the automorphisms of A, and the product as I goes from 1 to infinity, 1 minus L to the minus I. You can transfer information in ways that is even it has pull lots of places. Another kind of pull is not what your class group looks like, but whether you even have a G cover. Mala's conjecture is about the frequency of G covers for a given G and what that distribution looks like. So there's been this recent progress on cases of Mala's conjecture in the function field case. Cases progress on, let's say, progress on Mala's conjecture in the function field case. And this is due to Ellenberg, Tran, Westermann, Landsman, Levy, and then Wang and Wood show that various moments would compute. If you computed various moments of the distribution, it would prove the Cohen. It would prove. It would prove the Cohen-Lenstra heuristics. But so Ellenberg and Westerlund and Landsman Levy it's a little complicated to state what they prove. So let me not do that. But Mahle's conjecture itself implies the inverse Galois problem, and maybe I'll quickly write. Actually, maybe I won't write some things about Mahle's conjecture, but there's you want to bound densities of frequencies of Galois covers with Galois group G at bounded discriminant. So here's a fun example of Arnold of this kind of program in a transparent in a more visible case. So an example of the way you get control over how many covers you might have using topology, how many G covers, is that the Z2 Galois extensions of FQ of T with discriminant is the square root of something, and the discriminant has degree n. This is in bijective correspondence with square-free polynomials of degree n. Of degree n and FQ T, and by a result of Arnold, the configuration. So Arnold in 1970 computed the cohomology of the complex points of configurations of endpoints of C. And it's Q for I equals 0 to 1 and 0 for I greater than that. And this corresponds to the fact this has cardinality. Q to the n times 1 minus 1 over Q. So we're keeping track of Z2 Galois extensions through the cohomology of a configuration space. That's a very cool story just about the Weil conjectures themselves and about other people's work. But I'd like to make the point that transferring information between the complex points and other forms of math is a thing. So let's enrich the logarithmic derivative of the zeta function as follows. So we'll take K a field, and let's define. So this is joint with Bilou, Ho, Srinivasan, Voigt. So let X be, you could say smooth proper. You could get away with smooth, and let's just say be smooth proper. Over K, and F X to X, an endomorphism. Let's let d log d log 1 zeta of x zeta A1 xt xc be the power series where instead of taking the number of points over a finite field, we view that as a trace, but now we take the trace in the stable A1 homotopy category. So let's take the sum as m greater than or equal to 1 of the trace of f to the m, t to the m minus 1, where trace A1 denotes the categorical trace in SH of K, where that is, again, the stable A1 homotopy category of Morel and Blavatsky. So where this lives then is in endomorphisms of the unit. So this then lies in power series with coefficients in the growth and decay group of K. And again, just so that it's complete, we'll let I'll remind you that GW of K is the group completion of isomorphism classes of symmetric non-degenerate bilinear forms. And for finite fields, let's write down what this is of symmetric non-degenerate bilinear forms. Over K for a non-zero A, we'll again, let me remind you that the number in brackets A is the bilinear form, which takes xy to axy. And then we're most interested in the case of a finite field. So the growth and defit ring of a finite field is isomorphic to the polynomial ring on U, where brackets U is not a square. U is not in FQ star squared. And then it's multiplicatively, this is an isomorphism of rings, and the relations are that U squared is the same thing as 1, and 2 times U minus 1 is 0. That's because FQ, its fundamental group is Z hat, so it's a tall cohomology, looks like that of the circle, so it's non-zero in 2 degrees, 0 and 1. And the Milnor conjectures allow us to give a filtration corresponding to the tall cohomology mod 2 of this. So it follows from the Milnor conjectures that as a group, these first 2 invariants determine this entire growth and defit group. So as a group, this is isomorphic by the rank and the discriminant with Z cross FQ star over FQ star squared, where the discriminant is the determinant of the matrix with the corresponding to the bilinear form, and that extends to the group completion. So what we have here is an extra piece of Z mod 2 information for every single every single M. So let's do an example that will come up later. We had in the last talk a discussion of the relation between real and complex points, and we can use that to compute the degree of the Qth power map P1 to P1 when we compute traces. That's a degree of a map from the unit to the unit. You can compute them by what you do on cohomology groups, and if you wind up having pieces that look like smashes with P1, some fun examples that we'll write down we can write them down because we know the degrees. We know the following degrees. We've seen this diagram before, but if we have a degree from Pn minus 1, or we can also write that as homotopy classes with maps from P1 smash n, P1 smash n, so there's a degree lying in GW of K. And when K is in R, we can read off the rank and the signature from the action on the real and complex points. And so the degree of the Qth power map on P1 is going to have rank Q and signature 1 when Q is odd. And it has to be a bunch of 1s and minus 1s because everything's smooth and proper over Z. And anyway, there are other ways to compute that the degree of the map from P1 to, oh, here, let me finish writing this diagram again, but I got embarrassed because I showed it to you a minute ago. Okay, so the degree of the map P1 to P1 that sends Z to Z to the Q, it's going to be 1 plus minus 1 plus 1 all the way to Q terms. If Q is odd, as it probably is, then you'll end on a minus 1. But this number, this sum, as J goes from 0 to Q minus 1, minus 1 to the J gets its own special notation. This will be called Q of epsilon, and it's the degree of the Qth power map on a P1. Okay. So it follows from taking étale realizations that the rank of the logarithmic zeta function is the usual zeta function. So the rank d log zeta 1 x f is the classical d by dt log zeta xf, and we can calculate what these extra Z2 terms are from the enrichment of the Lefschetz fixed point theorem due to Hoywa. So Hoywa X smooth proper and let's say X F with isolated fixed points. Then the trace of f is equal to the sum over the fixed points of an index of f at the fixed points. If 1 minus f acts invertibly on the tangent space at x, then this index x of f is the transfer map that post-composes with the trace from Galois theory from the field of definition of the point of the determinant of 1 minus f prime of x. So the map on the tangent space, I guess prime, it's a little bit. There's an induced map on the tangent space, and the identity minus that, if that's really invertible, you could take its determinant, and then that would be a non-zero element of the residue field at x, and that's the index. So with the Frobenius, the map on the tangent space is always 0. So that means that the logarithmic zeta function can be written that implies that for x over fq, smooth, proper, and f, the relative Frobenius, then d log zeta A1 xf is the sum of I dividing m of let's let alpha I be the number of points of x with residue field fq to the I, so where alpha I is the number of points of capital X with residue field. FQ isomorphic to FQ to the I times this transfer map, the transfer from FQ to the I over FQ of 1. We've just written that all that we need to know is the rank and the discriminant. The rank of this is I. So the trace of FQ to the I over FQ is from Galois theory of 1. It has to have rank I, but then the discriminant, so this is the trace form, this is Galois theory, the trace form of the finite field extension FQ to the I. The discriminant of a trace form is the discriminant of a minimal polynomial, but we know how the roots of a minimal polynomial of FQ to the I, we know how the roots of a minimal polynomial are permuted. They're permuted as an I cycle. So when is an I cycle even? It's when I is odd. So this is I when I is odd, and it is I minus 1 plus u, our generator, the scalar that was not a square, when I is even. So this is entirely explicit. By Mobius inversion, so Mobius inversion means that these alpha I implies the data of the alpha I is the same, is equivalent to knowing the number of points f 2 to the I. So like the classical zeta function, this is some manipulation of all all of these numbers. But the extra z mod 2 has to be compatible with how you got it. It is a categorical trace in stable A1 homotopy theory, and it has to obey things like that because it's a categorical trace. Okay. It's a theorem of Xiaowen-Hu that the logarithmic derivative, the A1 logarithmic derivative is rational. Theorem of Xiaowen-Hu that d log zeta A1 x with the Frobenius over q f Frobenius is rational, and you can get computers to compute them. So, for example, with y squared equals x cubed plus x plus 5 over F13, the A1 zeta function d log zeta A1x t is 9 plus 170 plus u t plus 2,268 t squared plus 28,898 plus u t cubed, and this goes on and on. And there are different patterns for where the u's show up depending on which elliptic curve you take. So since you can compute these, you can find out that they are not coming from Kapranov's motivic zeta function, which puts in the K-naught varieties symmetric power of x as its replacement for the trace of the Frobenius to the m. So we have this Kapranov motivic zeta function x to the n t there are going to be some exps here. Actually, let me not just write it down. Sorry. But if you take the A1, what do I want to say? I think there's an X here. Does anybody, this is slightly wrong. Does anyone know it by heart? Well, you put the symmetric powers in the right way. And let me not try to remember. You can look it up online. But there's a motivic zeta function whose coefficients are in K0 of varieties. Like so, and the way one might try to recover the trace of Frobenius is that you could define trace of Frobenius on the varieties over FQ, and then the FQ points of the nth symmetric power, those are related to the FQ to the n points. So the natural guess would be that if you applied the trace of Frobenius to this, the A1 trace of Frobenius applied to Kapronoff motivic zeta function. We thought at first, actually, that was going to be the same thing as the definition that's still visible up there, but it's not. If you do this, you don't get any non-zero discriminant terms. So this actually lies in power series with z coefficients. So they're computably different.
What is work? I think your formula was correct.
Really?
Your original formula was correct.
Okay. All right. Great. Okay. My lucky day. Thank you. So this is not equal to d log zeta A1. X. Okay. It is, however, a motivic measure in its own right. So the d log zeta A1x defines ring homomorphism from K0 of varieties over FQ to power series with coefficients in GW of FQ. And that's called a motivic measure. In other words, it defines a ring homomorphism. And it also means it makes sense to talk about the logarithmic A1 zeta function for any variety. They could be singular. When they're smooth, it's going to agree with the fact that smooth things are dualizable once you invert the residue characteristic, which doesn't do anything to, it doesn't kill anything in GWFQ. So it'll actually just land in here. All right, so let's make our aim to connect the topology of now the real points of a lift to the solutions over a finite field of the defining equations. Aim connect the topology of XR to X Q to the M equals 1, 2, 3, and so on. By what we've just said, we would be just as good connecting to the topology of the real points to d log zeta A1 x of t. We can do that by using compatibilities of stable homotopy categories with base change and cohomology theories in the presence of extra data. So for one thing, if you started over R with an endomorphism, you have to be compatible with the real points. So joint with Bilu, Ho, Srinivasan, Hoyt, it follows from the diagram that's still up there that if you started with a smooth scheme over R, so for f x to x, an endomorphism of a smooth scheme over R, then the fact that you have the Betty cohomology of the real realization and that this respects the smash product going to the tensor product, it means you can compute the trace after applying Betty cohomology so that you have to get that the sign of d log zeta A1 xf of t has to be equal to d by dt log of the characteristic polynomials of the real realization of f. So the determinant of 1 minus t times f acting on hi r with q coefficients, with the odd ones in the numerator and the even ones in the denominator. When you're able to lift, and you can, for varieties like P1, then the same thing has to hold. Two, Fx over Fq is smooth proper, and a very strong condition, and you have a lift is a lift of x, and it's Frobenius to the ring of integers of some number field, then you get a lift. Is a lift of d log zeta x f t to the growth unique bit to a power series and with coefficients in the growth unique bit group of the ring of integers of the number field, which on pullback gives you your original zeta function. And if, for example, for toric varieties, you're just going to lift all the way to z. So if you have an embedding, for an embedding OK into R, then the lift is going to have to satisfy that equation. So we'll have that the sign, the signature of the lift is computed like so. So d log zeta A1. I'll make these things curly so that it's the A1 zeta function of the lift with coefficients in Hermitian K theory. Again, the signature has to be the logarithmic derivative of the characteristic polynomials of the way Frobenius acts, the lift of Frobenius acts on the real points. 1 minus t f xr q with the odds in the numerator. Okay. So for an example, the restriction of scalars, C to R of P1 and P1 cross P1 with the identity function being the identity function in each of these cases have the same classical zeta functions. Because the étale trace picking up the étale trace is picking up the Euler characteristic, and we have the C points of the restriction of scalars. And the twist are both S2 cross S2, but the R points are different. Here we get the shape of the C points of P1, that's an S2, and here we get an S1 cross S1. So they have the same classical zeta functions, but not the same, but unequal enriched zeta functions. An example where 2 holds is all toric varieties. So example where the hypotheses of 2 hold for X toric variety. And so then the Frobenius really lifts all the way to Z. I see him running a little bit short on time. So let me the proof of this is just the compatibility with pullback and having Hermitian K theory. But let me skip it, not because it's hard. a corollary is we have a funny criterion for a real point. Suppose that Q is congruent to 3 mod 4 to make it easier to state. 3 mod 4, then, and the hypotheses of 2 hold. So, and X satisfies those hypotheses. Hypotheses of 2 with a lift to Z with equals Z. Then, if you don't have any R points, this alternating sum of your numbers of FQ points has to satisfy an even or odd condition. So then if X of R is empty, it implies 2 congruence conditions, but for any M, so it implies that for all M, the discriminant of the sum of D dividing M of the number of points on X with residue field FQ to the D times this trace from FQ to the D, FQ to 1. But we know that this is just a formal manipulation of those number of points over various finite fields. So this discriminant is in FQ star squared if and only if X F Q to the M is a multiple of 4. We've got a whole bunch of these folks on the other side with some parity condition, and it has to be, it's got to be a multiple of 4, and it's not a square if and only if it's a multiple of 2. So, and furthermore, this same discriminant, so I'm going to use the, this quotations means this same discriminant is not a square if and only if this is even. Congruent to 0. Mod 2. So this is a congruence condition on the number of solutions over FQ to the I as I goes from 1, 2, 3, etc. And
you mean not congruence?
Sorry. Sorry, congruent to 2. Thanks. Thank you. So this is a constraint mark. This is a constraint, one constraint for each M. There's a bunch of constraints on X, F, Q to the M. And P2 violates these. It's a congruence constraint, which does not hold for P2. Or the Grassmannian 1-3. So you could tell, not that you couldn't already, that P2 has to have a real point just by looking at the number of its solutions over finite fields. So we can also get lower bounds on Betty numbers. Lower bounds on Betty numbers for the real points. Again, under the hypotheses of the corollary. Okay, I've got 1 minute remaining, and I wanted to just do an example. You go 3 minutes over. Okay, and then let's use the degree that we computed, this 1q epsilon, to do the zeta functions in terms of a cohomology theory, which we won't define, but it's Morel and Savant's. Okay, so let's take the restriction. Here's an example of how to get lower bounds. We'll take the restriction of scalars from fq squared over fq of p1. So for example, we could have x was the quadric 5x naught squared plus x1 squared plus x2 squared plus x3 squared equals 0 in P3 over F7. And then what the logarithmic A1 zeta function is it looks like P1 cross P1 in the 0 and 2 cell term, A1 xt. So d by dt log. Here we've got 1 minus t from the 0 cell, and 1 minus q epsilon squared t from like the P1 cross P1 cell. And then the terms from the instead of the P1 cross P1, you kind of have 2 cells, and they're kind of mixed up with each other because they've got this Galois action. And what they contribute when you take a certain cohomology theory and you take its trace on a cool little matrix, what you get is minus u dt log 1 over 1 minus q epsilon u t. U is a non-square in fq, plus minus 1 d by dt log 1 over 1 plus q epsilon t. Now let's take q congruent to 3 mod 4, then minus 1 can be u. So let's take congruent to 3 mod 4, so we can take u equals minus 1. We can lift this by restricting scalars for an appropriate extension of number of q, add the appropriate square root. And so then it makes sense to take the sign as in part 2. So we can take the sign of d log zeta a1 x t, and that is 1 minus t times I guess q epsilon is going to have sine 1, so is q epsilon squared, so that looks like d by dt log 1 over 1 minus t squared. But then this term, the minus u, that's now a plus 1, and that's a minus 1, and this minus and minus make these two the same. So these two terms cancel out entirely. So that's it. That's what you get as your sign. So that means that your Betti numbers, B0 plus B2, they have to be at least 2. But these are for your real points. These aren't your complex points. 0. So we're taking information about the number of solutions of equations over finite fields and concluding things about the topology of R. In my last negative 1 minute, I promised this application. So how do you read off the d log zeta? These are visible of, say, Pn. Well, it's d by dt log, and then you want the characteristic polynomial of Frobenius kind of acting on the ith cell of Pn, which is kind of like a pi to the n. So you're taking a trace on like pi, P1 wedge power I. So this becomes q to the I epsilon, because using the A1 cellular homology of Morel and Savant. Thank you very much. I'll stop there.